AS Unit 1, Topic 2, and we're going to look at electronic configuration. This is a part of the specification for Topic 2 that deals with electronic configuration. At GCSE, we learnt that electrons are found in shells. The example on the board is sodium, and sodium has 11 electrons and 2 fit in the first shell, 8 in the second and 1 in the third shell. At AS level, we are going to look at energy levels, subshells and orbitals, and we will learn a new way to write the electronic structure of sodium. It will look like this: 1s2, 2s2, 2p6, 3s1. So we need to learn more about energy levels, subshells and orbitals. Electrons are arranged in energy levels, which we would have called shells at GCSE, in which the energy of the electrons increases with increasing distance from the nucleus. If we look at the left-hand side, we can see the first 4 energy levels, or the first 4 shells, as we would have referred to them at GCSE. Within each energy level, there are subshells, and each subshell has orbitals. If we look at the first energy level, it has one subshell and it is made up of one s orbital, and an orbital holds 2 electrons. If we look at the second energy level, we have an s subshell and we now also have a p subshell, and a p subshell is made up of 3 p orbitals. If we move on to the third energy level, we have an S subshell, a P subshell and a D subshell. The D subshell is made up of 5 D orbitals. And finally, energy level 4 has an S, a P subshell, a D subshell, and now also an F subshell. And an S subshell has 7 orbitals. So if we look at the subshells in more detail, we can see that an S subshell only has 1 orbital, so it can only hold 2 electrons. A P subshell has 3 orbitals, so can hold 6. A D subshell has 5 orbitals, can hold 10 electrons, and an F subshell has 7 orbitals, so it can hold 14 electrons. At AS level, we need to know the shape of certain orbitals. The S orbital is spherical and the P orbital is shaped as a dumbbell. We will only be asked to draw the S and the P orbitals. In each orbital, we will find 2 electrons. We will start to draw what is called box notation, where a box represents an orbital, and we'll see that later on in the video. In each single orbital, electrons spin in opposite directions to minimize repulsions, and we represent this by arrows going up and down. Same spins are not allowed. Let's go back and see if we can now write new notation for the electronic configuration of sodium. At GCSE, we knew the electronic configuration was 281. Now at AS level, we're going to put in information about the energy levels, the subshells and the orbitals. So in the first shell or energy level, we have one subshell, the S subshell, which is 1 orbital holding 2 electrons. If we move on to the second shell, we have 2 subshells, the S subshell, which has 1 orbital and holds 2 electrons, and the P subshell, which has 3 orbitals, each holding 2 electrons, which means the subshell can hold 6 electrons. That will give us 10 electrons, so our last electron goes into the third energy level and into the S subshell first. That now gives us our new electronic configuration for sodium of 1s2, 2s2, 2p6 and 3s1. Here is the electronic configuration of the first 20 elements in the periodic table. If you have a look at the table, you will see that there is a systematic way of filling the subshells. We start with the 1s subshell, then we fill the 2s, the 2p, 3s, 3p, and then we move on to the 4s. If you look at the numbers in superscript, If you add those numbers together, you will find you will get the total number of electrons for that element. The example being sodium, where you add 2 plus 2 plus 6 plus 1 to get 11 electrons. We can write the electronic configuration as we have discussed, for example 1s2, 2s2 and so on, or we can actually illustrate it using box notation where the boxes represent orbitals. So if you have a look, you can see we have here orbitals for each of the subshells. We sometimes can also see this drawn horizontally as well as vertically. The rules for filling the boxes are as follows. Electrons are added one at a time to the lowest available energy level, so we would start with 1s. An energy level must be full before electrons are added to the next higher energy level. In a subshell, for example the 2p subshell, each orbital must be filled individually before any pairing of electrons can begin. Each orbital can hold a maximum of 2 electrons, and we must put in the electrons having opposite spin. If we have a look, here is an example of carbon. Carbon has 6 electrons. Its electronic structure is 1s2, 2s2, 2p2. So we put 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, and we fill in the 2 electrons singly into the 2p orbitals. Here is another example. You might want to pause the video and try this yourself. Oxygen is 1s2, 2s2, 2p4 because it has 8 electrons. So we put 2 electrons in the 1s, 2 electrons in the 2s, 4 electrons go into the 2p, so we fill it singly and then we start to double up. If we look at elements 1 to 20, we can see that the order of filling of the subshells is 1s, 2s, 2p, 3s, 3p and 4s. You might have noticed there that we are missing the 3d subshell. Why is that? If we look at the right hand side and the diagram of the energy levels, you will see that the 4s energy level lies at a lower energy than the 3d energy level. That means that we actually fill the 4s first and then we fill the 3d energy level. That means once we pass calcium, we enter the transition metals and you will find that we start to fill the 3d subshell. So scandium has 1 electron in the 3d subshell, titanium has 2, and vanadium has 3, and so on. What you will notice when we write our electronic configurations of the transition metals, we keep the 3d with the other 3 subshells rather than putting it at the end. So we keep the third subshells together. There are 2 exceptions that we have to learn, and that is chromium and copper. If we initially do our electronic configurations, we would expect chromium to have 4 electrons in the 3d subshell and a filled 4s subshell. However, its electronic configuration is 3d5, 4s1. One of the electrons in the 4s subshell is promoted to the 3d subshell. That means that instead of having 4 electrons, you have 5 singly filled orbitals in the 3d subshells. With copper, we expect copper to be 3d9, 4s2. But again, what happens is one of the electrons is promoted from the 4s into the 3d subshell. This now means you have a full 3d subshell. In both of these cases, the half filled subshell and the filled subshell means that there is more stability in these structures. If you find the order of the subshells difficult, this diagram, called the Aufbau diagram, does help. What happens when we fill the 3D subshell? So for example, zinc has a full 3D subshell. If we have a look at an element further along period 4, for example bromine, you will see that we start then to fill the 4p subshell, and bromine would have 5 electrons in the 4p subshell. We also have to look at electronic configurations of ions. When an atom gains or loses electrons to form an ion, the electronic structure changes. So for example, positive ions are formed by the loss of the electron. So an example here would be a sodium atom, which we've already looked like, becoming a sodium ion. So it loses the 3s1 electron. If we look at negative ions, the example here is oxygen becoming oxide. Oxygen has an electronic configuration of 1s2, 2s2, 2p4. So we need to give it 2 extra electrons to get a full outer shell. Notice that sodium and the oxide ion have the same electronic structure. Ions that have the same electronic structure are referred to as isoelectronic. What happens with the electronic configuration of transition metal ions? With transition metals, we tend to lose the 4s electrons first when we form ions. So for example, if we look at titanium, when we form titanium 2+, we remove the 4s electrons first. Here's another example. This is chromium, which has the electron arrangement 4s1, 3d5, so it has a half-filled subshell. When we form chromium 3+, we take 3 electrons away. We take the 4s electron away, and then we take the electrons from the d subshell. The last part of the specification expects us to be able to classify an element as belonging to the S, P, D or F block according to its position in the periodic table. There are 4 main blocks in the periodic table, and these are all based on the subshell in which their outer electrons are located. So for example, our transition metals, which we refer to as D block elements, all have outer electrons in the D subshell.